Hello everyone. Today we are going to discuss a very important property in fluid mechanics, that is viscosity in detail. As we know, viscosity is the resistance offered by one layer of fluid over another. So in detail we are going to discuss now viscosity as a property of fluid. So let us consider this left side diagram, which shows that there are two plates. One is fixed, one is moving with the velocity v. So this bottom plate is fixed and this top plate is moving with the velocity v meter per second. The area of the plate is A. The force with which it is moving, or because of which it's moving, is F. These two plates are separated by a distance, let's say L, or it may be anything, so I can take Y also. So let us consider these two plates separated by a small gap of Y. Considerably, these two plates areas on lengths are very large, and this thickness of the plate is very small. So you can observe these are the different fluid layers, and which I can say as a shear force exerted on these fluid layers. So when at this condition, at the plate, bottom plate, velocity is 0, v is 0, because this plate is stationary, whereas for this plate velocity is equals to exactly velocity of the plate, means I can say for this fluid layer velocity is equals to v, whereas the velocity for this fluid layer is approximately at 0. So this variation of a fluid velocity, this profile I can see is the velocity gradient. So variation of this velocity across the height or the gap of this oil film thickness is the change in velocity du across or along the height of the plate, let's say dy. This is a velocity gradient, a very important term. Why velocity gradient? Because velocity is changing with respect to the height of the plate or height of the film thickness. Instead of plate, you can say this is the gap of film or liquid fluid present between the two plates. So this is velocity change du with respect to the parameter y across the plate. Now same is represented here on this side. This is another plate which is fixed over this oil or any fluid is flowing. So I can say at this point velocity is 0. The variation is represented like this. So the change in velocity du across this height or across this oil film thickness y, this du by dy I can say as velocity gradient. And as we know, this is the shear force exerted on fluid layer, and this A is the area. So tau is shear stress. So we'll discuss these resistance offered by a fluid layer along the thickness or along the height of the oil film thickness, how it will explain a very important term as a dynamic viscosity. So what Newton's law suggests about that we'll discuss. So what is the Newton's law of viscosity, which introduced a very important new term called as dynamic viscosity. So Newton's law simply state that a shear stress between adjacent fluids, that means tau, is directly proportional to velocity gradients between the two layers. That simply means, I can explain with again same diagram here. Shear stress tau means that's force upon area. This shear stress is directly proportional to velocity gradient. So Newton's law suggests that statement is this shear stress tau is directly proportional to velocity gradient. That means simply it is du by dy. This is a Newton's law statement. Shear stress directly proportional to velocity gradient, which is also called as this velocity gradient is also called as rate of deformation. Rate of deformation. So now here we'll discuss in detail this shear stress tau is directly proportional to velocity gradient du by dy, means change in velocity with respect to thickness of the fluid layer. Then that constant of proportionality, if I to remove this sign, I need to use constant of proportionality, which is called as mu. So tau is equals to mu into du by dy. This is Newton's law of viscosity, where this mu is the constant of proportionality, which is called as dynamic viscosity or only viscosity. Dynamic viscosity. Very important term in fluid mechanics. Viscosity, which is always represented dynamic viscosity by mu, which is given by Newton's law of viscosity from a simple experiment or simple you can say example of a flow or a fluid flow over a plate. So that is shear stress is directly proportional to rate of deformation or velocity gradient, that is du by dy. So I can say this du by dy is the rate of deformation or velocity gradient. Tau is the shear stress. The constant of proportionality is the new term which is important, dynamic viscosity. Now this dynamic viscosity units as dimensions very important. It is in the term Newton second per meter square. How it is so? Very simple. I am using different things to remember. So see, for mu, how this unit comes? Newton second per meter square. This is SI unit for dynamic viscosity. Mu is equals to tau divided by this whole term. So I'll just write the unit for tau. Tau is the shear stress. So unit of the stress is Newton per meter square. Whereas what is the unit for this term? U is a velocity, so unit will be meter per second divided by its parameter, means across the height of the film, so that is it is meter. So this meter get cancelled out, so what remained is per second. So unit for mu is equals to this tau divided by this tau unit divided by this term unit. So this term unit is per second. So this per second goes here and this unit becomes Newton second per meter square. So unit for dynamic viscosity is Newton second per meter square in SI. For CGS system, I can say this dynamic viscosity can be represented in another term called as poise. P-O-I-S-E, poise, which is equals to 1 poise is equals to 1 gram per centimeter second. So normally you should know this thing, what is 1 poise and the conversion. So let us say we'll discuss conversion, which is very important. To convert this SI unit, the SI unit of dynamic viscosity is Newton second per meter square. So we need to know conversion. So 1 Newton second per meter square is equals to 10 poise. So this conversion we required for some numericals for solving simple topics or simple numericals on viscosities. Now, after that, one very important thing which we are going to discuss is viscosity types. So once you are clear with the concept of absolute and dynamic viscosity, another viscosity type you can say, which is called as kinematic viscosity, which is again simple formula. Kinematic viscosity, so I'll write here kinematic viscosity. There is a small relation between a dynamic viscosity mu, and kinematic viscosity nu. So this kinematic viscosity nu is equals to dynamic viscosity divided by density or mass density of the fluid. In some of the numericals you require this kinematic viscosity formula, so we are introducing this term. Now what is the unit for this? The unit for kinematic viscosity, as you know, it is absolute or dynamic viscosity, or viscosity divided by mass density, and you know the unit of mass density is kg per meter cube. The unit for this is meter square per second. This is SI unit for kinematic viscosity. Similarly, so I'll represent once again this. Nu is equals to dynamic viscosity divided by rho. So the unit for this is meter square per second. This is SI unit for kinematic viscosity. So this kinematic viscosity you required for some numericals. This is SI unit, meter per second. Now another unit, that is conversion in CGS, I can say it is simply, you can know, it's centimeters square per second, which is represented as Stoke, similar to poise. For absolute or dynamic viscosity we represent it is poise. For kinematic viscosity it is Stoke. So 1 Stoke is equals to this centimeter square per second. Therefore, to convert meter square per second into Stokes, that is in CGS system, I need to multiply with 10 raised to 4, that is 10 raised to plus 4, 10 raised to 4. 1 meter square per second is equals to 10 raised to 4 Stokes. So this conversion is required for few numericals.